mutually exclusive events. So when you're dealing with mutually exclusive events, so probability of A and B will be 0. Okay, so the total probability of A and B will be 0. So when the events are mutually exclusive, then the additional rule can be simply, so probability of A or B will be probability of A plus probability of B. So this rule is important, and you need to pay attention on this rule. All right, so then we look into the conditional probability. So when you are dealing with more than 2 events, so then we can define conditional probability. So conditional probability means the probability of one event occurred, then we are calculating the probability of other event. So when we write like this, so probability of A, given that B, the event B has occurred. Okay, so this is, we call it as the conditional probability. So the event B has already occurred, then based on that information, we are calculating probability of A. So the rule for this is probability of A and B over probability of B. So this is known as the conditional probability. So we can also write conditional probability in the way shown here. So in this case, we know probability of A. The event A has already occurred. Then we are calculating the probability of B. So probability of B, given that event A has already occurred. So this can be written as probability of A and B over probability of A. So these are the rules related to conditional probability. All right. Okay, we have looked into examples. So we can also calculate conditional probability from decision trees. Okay, so when 2 events are independent, so we are defining another scenario where 2 events are independent. We have defined what is meant by mutually exclusive, collectively exhaustive, and now 2 events can be independent when the conditional probability of A given B has occurred is equal to probability of A. So that means the events A and B are independent when the probability of one event is not affected by the fact that the other event has occurred. So for example, when you toss a coin, the probability of getting a head or tail is 0.5. So when you take another coin and toss it, so the probability of first result is not affected for the second trial. So we can say that the 2 events are independent. All right. So we have looked into this. Then the multiplication rule we can write for 2 events. So this the first multiplication rule. Okay. Then when from this we can also write probability of A and B is equal to the conditional probability of A given event B has occurred multiplied by probability of B. All right. So I clear this. Okay. So this is how we can calculate simple probability rule. Okay, ethical issues, then Bayes theorem, we have done last session. Okay, Bayes theorem is not important exam point of view. So exam point of view, mostly how to calculate empirical probabilities. So I go through. Okay, next, we have looked into counting rules. So counting rules are important to find out the total sample space. So sometimes when you are dealing with events, so we'll be having a large sample space. So we can find out the sample space based on the simple counting rules, which we can go through here. So there are 5 rules. So the first rule is when we are Okay, so when the event has k different mutually exclusive and collectively exhaustive events. So for example, when you toss a coin, so the probability will be either head or tail, so k will be 2. Okay, and n is the number of trials. So for example, if you throw a coin 3 times, so what will be the sample space? So the sample space, we can write it as 2 cubed. So 2 is related to k, okay, and n is number of trials. So here in this example, you can say that when you throw a fair die 3 times, okay, so the sample space will be 6 to the power of 3. So 6 is the probability for the sample space for the one die. Okay, when you throw 3 times, the probability, the sample space will be 6 to the power of 3. All right. So the next one is the counting rule when we are dealing with K1 events in one trial and K2 events in another trial, etc. So the total sample space will be the multiplication of all these events. All right. So then the counting rule 3 is the number of ways in which n items, okay, here n items that can be arranged in order, okay. So here this is in order. So here we write this as factorial n. So when we write this as factorial n means n into n minus 1 into etc. up to 1. Okay, so here I told you that for factorial 0 is considered as 1. Okay, so for example, if you have 5 books to put on a bookshelf, so how many different ways you can place this? So the answer will be factorial 5. So factorial 5 means 5 multiplied by 5 minus 1, that is 4, multiplied by 5 minus 2, that is 3, then okay, 2, then 1. So factorial 5 is 120. All right, so then permutations, the rule number 4 is about the permutation. So here we have 2 things. One is X number of objects you want to arrange from a sample of n objects. Okay, and the order is maintained. So here the rule is, the counting rule is n probability, n permutations x. So we read it as npx. So npx is written as factorial n over n minus x factorial. So for example, if you have 5 books and you're going to put 3 on a bookshelf. So here your n is 5 and x is 3. So the number of permutations will be factorial 5 over 5 minus 3 factorial. So factorial 5 in the previous example we have seen as 120. So 5 minus 3 is factorial 2. So factorial 2 is 2 into 1, therefore it is 2. So the answer here is 60. So the sample space in this scenario of arranging 5 books, okay, 3 on a bookshelf. So you pick up 3 books from the 5 books. All right, I clear this, then move on to the next one, the combination. So this is the important one for us. So when we calculate the combinations related to, again, X objects, okay, from N objects. So we are choosing X from a sample of N. Here, the order is not important. So the order of arrangement is not important. So here we read this as NCX. So NCX is factorial N over X factorial multiplied by N minus X factorial. Okay, so this is how we can count when we are dealing with combinations. Okay, combinations of X objects from a sample of N objects. So we can see the example here. I move on from here. Okay, so we have looked into the summary. Then, so the essence of probability which we have seen is Okay, whether we are dealing with one or two variables. So if you are dealing with one variable, so we are dealing with simple probability. So if there are more than two variables, the probability can be joint probability. So here it can be A and B, or it can be A or B. Okay. Then for two variables or more variables, so we can also have conditional probability. So an extension of conditional probability is Bayes' theorem. All right. So this is the summary of this topic, and all these things we have done in the last session. It was a recap. So now let us do some examples here. So I expect some response from you. Okay, I take out my camera. All right. So can you answer the okay, the first question, the 3 coins are tossed. Okay, so give an example of a simple event. So the simple event, you can define either this as the probability of getting a head or getting a tail. So that will be the simple probability. All right, I think Chika is asking the question. Okay, it is there in the study guide, and okay, I'll show you maybe after the break. All right. So the assignment question is open-ended assignment, and I can go through. Maybe after the break, I'll show you where you can find the assignment. All right. So now let us look at this question. So 3 coins are tossed. So what is an example of a simple event? So an example of a simple event you can see as probability of getting a head or probability of getting a tail. Okay, an event can be, okay, tossing a head or tossing a tail. Now give an example of a joint event. So when you're tossing 3 coins, okay, so joint events can be, so tossing 3 heads, or 1 head and 2 tail, or it can be 1 tail and 2 heads, or it can be 3 tails. So this is an example of a joint event. Now, what is the complement of a head in the first toss? So the complement of a head is that tossing a tail on the first toss. So then the D, what does the sample space consist of? So here, so when you are tossing 3 coins, right? Each toss can result in a head or tail. Okay. So you can say that all the 3 resulted in head. So this is one event. Or you can have first 2 events tosses head, and the last one is a tail. So you can have the first toss head, second toss tail, and third toss head again. So like this, so you can see all the sample space events. So the 4th one can be a tail, head, and head. So the 5th one can be tail, tail, and head. So the 6th one can be tail, head, and tail. So the 7th one can be head, tail, tail, and the last one can be all tails. Okay. So here, this one, we can calculate the number of sample space simply by applying the first rule. So 2 to the power of 3. So here, the probability of getting, when you toss a coin, so either head or tail, so there are only 2 outcomes. So since you are doing 3 coins, you're tossing it, so the sample space will be 2 power 3. So 2 power 3 will be 8. So you can also visually write down all the different outcomes of tossing 3 coins. All right. So any question on this? Is this okay? All right. So then let us move on to the next Okay, now let us look at this contingency table. Okay, then there is events A and complement of event A dash. Okay, so this is event A and this is the complement of event. So this is event B. So this is complement of B. Okay, so here the total will be 30. So here the total will be 30. So here the total will be 60. So here the total will be 60. And the total combined sample space is 90. All right. So can someone tell me what is the probability of A? So what is the probability of event A? So anyone? 0.33 is correct, but how do you calculate? So probability of A is, so we write the total 30 over 90. So you can write probability of A is 30 over 90. So you get this as 1/3 or 0.33. That is correct. Then what will be the probability? Is the probability of A complement. Clear this. So this is A complement, probability of A complement. So probability of A complement means, so you need to see here, this A complement is 60 over 90. So the second one will be 60 over 90. I think you guys very young and Chikai correct. All right. Next, what is the probability of A and B? So A and B, now we can see that this is A and B. So it is not 30 over 90. So A and B is 10, okay, over 90. So the probability of A and B, we can write it as 10 over 90. So that is 1 over 9. All right. Next, the probability of A or B. Probability of A or B, you need to apply the formula. So you need to apply the formula, probability of A plus probability of B minus, so probability of A and B. So you need to apply the formula. So probability of A is, we have seen 30 over 90. So this is the probability of A. So plus probability of B. So probability of B is again 30 over 90. Minus probability of A and B. So probability of A and B negative is 10 over 90. So if you do this, okay, 90 denominator is common. So we can just write this as 90. Then we can just add up 30 plus 30, 60 minus 10. So the probability is 50 over 90. All right. So the probability of A or B is 50 over 90. Guys, any questions, any doubt, let me know. Is that all right? Okay, I clear this, then how to get answer D. So to get answer D, you need to apply the, I go through the formula. So the formula is A or B, okay? So you need to apply this formula. So probability of A or B will be, so probability of A plus probability of B minus probability of A and B. Okay, so we have seen that for the given problem, so probability of A is, probability of A complement and B. Let me go through. So I quickly, so if the problem is A complement and B, you need to look for 20 over, okay, 90. So this is A complement and B. Again, you need to apply the same rule. When you have A complement or B, so you have to apply the rule probability of A complement plus probability of B minus probability of A complement and B. Is that clear, Tekmeng? All right, so that's it. And normally in the exam, you might be asked, because this is based on the table data. So these type of probabilities are important, how to calculate. Now let us look at this example here. So here we are talking about generation X and boomers. So where there is a two different events. One is generation X and we are having boomers. So generation X means the people who are born in 1970s. And normally that means between 1965 to 1980. So people born between 1965 to 1980. So they are known as generation X. So boomers means those people who are born during the population boom. So that is during 1955 to 1964. This is just out of curiosity I'm giving you. So some of you may not be knowing what is meant by generation X and generation. So generally now I'm belong to this group, boomers. Okay, so the people who are having around 60 plus years, less than 80, 70. All right. So this question is about how the two generations of people use their credit cards. So the sample size of 1000 generation X and 1000 boomers. So the result of this is shown here. Okay. So the results shows that those who pay full amount every month. So out of 1000 generation X, 440 people would pay full month, full credit card bill every month. But from boomers, it is 630. So there's a total of 1070 people pay every month out of 2000. So those who don't pay, okay, from generation X, there is 560, and from boomers, it is 370. So total 930 people, they don't pay every month, okay, full amount. So the total sample space is 2000. All right, once you understand this, I'll give you few minutes. So can you answer the first one? Those who pays the full amount, probability of pays the full amount each month. Anyone? So probability of who pays full. Don't give me the percentage. You can calculate the percentage based on the figures. Of course, your answer is correct on. So it will be 1070 over 2000. So this is a simple probability. Okay. So that gives you 0.535 or 53.5%. Okay. So that is for part A. So you can expect similar questions for the your end of term exam. Now, the part B. So is a generation X and pays the full amount each month. So what is the probability of generation X and pays the full amount? So it is a joint probability. So generation X, you have to look, and also you have to look pays the full amount. So can someone give me the answer? So is this, okay, so this is generation X and pays the full amount. So yes, you're right. So it is 440 over 2000. So we can write the probability as 440 over 2000. Yeah, that can be 0.22. The next one. So this part C is you're looking at generation X or pays the full amount. So this is a, yeah, you need to apply the addition rule. So part C, you can try. I think the question and answers I can be shared once we complete the Saturday session. So we'll be able to share the questions. Yeah, the answer is 0.815 is correct.